Well, welcome. We're going to take a look at Chapter 7 applications today. Before we get started, we got a bell ringer, just a review question from parabolas. And specifically, we're going to have to write an equation. Now, as I've kind of been mentioning the last few classes, that in the state of Texas, the thing it's expected of you is to be able to write an equation for certain different conic sections. In this case, I'm looking at a parabola. And so what I would recommend for you is to follow the formula chart that we have. You open this up, and also today I'm going to be using some Desmos, so I'll open up just a pre-programmed graph there. But I'm going to open up the formula chart on this tab, and I'm going to go to parabolas. Where are they? There we go, second page, parabolas, and I'm going to copy down the basics of what I know is true. And what I know is true is that we're going to have a parenthesis squared equals 4p times another parenthesis. So we will have 4p, or excuse me, a parenthesis squared equals 4p times another parenthesis. That's what I know is going to be true, regardless of the information given to us. Now, talking about that information, let's see what they did give us. They gave us a vertex, which for a parabola is your h and k. So this vertex is going to end up being our h and our k. And they also gave us a focus. For review, for real world problems, that's like the reflection point. Reflection point of a parabola. Now I can actually determine a lot from this information or the formula based off of these 2 points. When you compare and contrast them, which value is staying the same, the x value or the y value? The x stays as -2. What is that telling me? That means that both of the x's are the value h. So on the second point, the -2 must still be h because it's not changed. But the y value has changed, so it's not going to be simply put k. It's going to be something different. So if I go over to the formula chart and I look at both options, this is our horizontal parabola, this is our vertical parabola. If you look at the focus underneath each one, and you'll see that on the horizontal parabola, it's the x value that changes, that be h plus p. But on our case, we will need the y value to change. So it's going to be everything listed on the right side. This is going to be k plus p. That's what this value is going to represent here. This change it. Value is going to be k plus p. And we now know that since it's a vertical parabola, you would have y minus k in this parenthesis and x minus h in this parenthesis. As you kind of get that there, I'm going to give you a second to write. The reason, if you wanted to memorize the formula, that the focus is next to y is because the focus is moving up and down. If you plot at this point, the vertex would be left 2, up 1. There's the vertex. The focus is left 2, down 5. 1, 2, 3, 4, and 5. If it's down 5 like this, you can see that the focus or the p-value would be negative because this is a negative parabola and the focus is moving downward. It's moving downward. That's why the p is next to the y. Okay, having said that, let's go in now. Hopefully you've kind of caught up with me. I'm going to plug in the h value, and remember h is going to lie, and the reason we say that is because a -2 is going to replace this h right there. And so it becomes x minus a -2, and 2 negatives make a positive. So it's actually going to just be x plus 2. And then on our second parentheses, our k value is 1. So when I substitute that in, it'll be y minus 1. Inside lies. And now the question, how would I solve for p? Well, here's my p. It says that -5 equals k plus p. -5 is going to represent k plus p. Well, we just solve for k right here. So I don't have to leave that as a variable. I can say, oh, I know what k is. K is 1. Which means -5 equals 1 plus p. So how would I solve? I would subtract. So -6 would equal my p. If negative 6 equals p, what is 4p going to equal? Negative 24. So we can plug that in right there. And that would be our bell ringer. All right, today we're going to actually check out lesson, what I call 7U or 7 applications. What we're going to look at is all the 4 different conic sections we've dealt with here. Ellipses, circles, parabolas, and hyperbolas, as well as we're going to take a look at projectile motion at the very end of the lesson. So we're going to review all of chapter 7. When we started chapter 7, I said, why do we call these things conic sections? It's because these are sections of a cone. Sections of a cone is why they call it that. Now, this picture isn't my favorite, but it's in color, so I took it. Here's what I want you to know. How do you form an ellipse? Typically, if you were going to test this, someone might say, well, it would be a plane intersecting the slant, and they would call it being perpendicular to the slant. The plane would be intersecting perpendicular to the slant. So here's what you need to know about an ellipse, is that it could be created if a plane intersects perpendicular to the slant, it will always form an ellipse. Perpendicular to the slant. If a plane intersects perpendicular to the slant, it will form an ellipse. The circle here is created if a plane intersects parallel to the base. That's how we form a circle, is by taking a plane and intersecting a cone parallel to the base. And it must be parallel to the base. A parabola, though it could be formed many different ways. If you look on here, this back part of the plane is parallel to the slant, and that's how we're going to form a parabola. Say it will be parallel to the slant. So again, a lot of these shapes don't have to be perfectly perpendicular to the slant or parallel to the slant to still form ellipses or parabolas or hyperbolas. But the one thing that does have to be perfectly true is the circle, and that's why it's a red plane here, has to be parallel to the base. Now, why I don't like this picture is it doesn't really work well with my verbiage here that I'm about to use, but it is true that if you are perpendicular to the base, you are always a hyperbola, perpendicular to the base. Now, it doesn't have to be, like I was just saying, on 3 of the shapes, they don't have to be perfectly perpendicular or parallel. But if they happen to be perfectly perpendicular to slant, it has to be an ellipse. If it's parallel to the base, it must be a circle. And only a circle if it is parallel to the base. That's the only one that has to be exact all the time. Parallel to the slant. If you are parallel to the slant, it will be a parabola. But it doesn't have to be perfectly parallel to still be a parabola. And the same thing with the hyperbola. If you look at this, this is not perpendicular to the base. This image is obviously not perpendicular, but it still created a hyperbola. However, if the plane was perpendicular to the base, it would have to be, and only could be, a hyperbola. So that's kind of the verbiage. If you were going to get tested without the pictures, but just the verbiage, that's the verbiage that would be used. So I kind of want to review that. Now, how are we going to review all of chapter 7? Real world problems. Why not? It'll be the best. So let's first take a look at a parabola. So before I start the real world, here's your points that we talked over. The axis of symmetry, cut everything right through the center. You have a directrix for if you were building, say, bridges or anything like that, that would be where you would place the road. It's a source of strength, if you will. The focus, if you're using anything that's dealing with reflection, whether sound waves, light waves, gamma radiation, anything doesn't matter. The focus is the point of reflection. That was what we used for parabolas. So example 1 says, the mirror of a flashlight is a paraboloid of revolution. 3D parabola. Paraboloid of revolution is just a 3D parabola. Its diameter is 6 centimeters across, and its depth is 2 centimeters. How far from the vertex should the filament of the light bulb be placed for the flashlight to have its beam run parallel to the axis of its mirror? The question is essentially saying this: where should we place the light bulb so that the light shines out at like a beam, like a flashlight's light should shine? And so if you remember me saying in this lesson, we went over it, the light bulb needs to be reflected. What makes it come out like a beam is not that you have a special light bulb, it's that it reflects off this paraboloid revolution. So for this to be reflecting, it needs to be at that reflection point, which we called the focus. Very good, the focus. So we need to place that light bulb at the focus. The focus is going to be somewhere within this parabola, but it'll not be outside the glass, obviously. You got to have the light bulb on the inside. So that's where it's going to be located. So what is step one? Well, what we were doing all this chapter is the first thing we do is go copy the blank formula. We know that for a parabola, you'll have a parenthesis squared equals 4p times another parenthesis. Now, from here, we can look at this image and tell that this parabola is opening to the right and the focus is moving. It's going to be somewhere either to the left or to the right. Well, it's obviously going to be to the right of it, which means 4p needs to go next to the letter x because 4p deals with my focus. So this is going to be next to the letter x, and this is going to be the y over here. So on my formula chart, I can fill this in and say, okay, if the focus is moving left and right, it goes next to x. So this is my equation. So we can throw on there y minus k, x minus h. Now that's where we always started first. And then we would fill in information from the mathematical problem. Well, with real world, a lot of times they don't give us the same mathematical information to plug in, so that's kind of a disadvantage. But what is an advantage is we get to just kind of make up, since this is not placed on a graph, we can just make up some information and base everything else from it. What do I mean by that? Well, let's just take, for example, the vertex. The vertex of this parabola is always labeled h comma k. The problem doesn't tell us where the vertex is located. So we could just say, hey, let's make our math simpler and call the vertex 0, 0. Let's just call that point 0, 0. What does that do for my problem? Well, I now substitute zeros here. And since y minus 0 or x minus 0 is still y and x, I can simplify my formula to be y squared equals 4p times x. Y squared equals 4px. So that was helpful. And now for the first time we get to see this. We haven't done this in any of the lessons. What do the x and y actually represent? The x and y represent any point that's on the shape itself. So we're dealing with a parabola. That means any point on this parabola could be represented by the x and y. I'm going to take this top corner right there. And we could choose this bottom corner, but I'm going to choose the top corner here. Maybe we'll do both just for the practice. If we were going to list this as an x comma y, you would need to list it in relation to this point 0, 0. So that point is to the right. How far to the right is this purple point from the green point? How far to the right? 2 centimeters. So I'll put a 2 there. And how much higher is this point in purple in comparison to the point in green? So I hear 6 quite often. It's not actually 6. 6 goes all the way across. It's kind of like 2a there, thinking your diameter. So what's half of it? 3. This will be 3 up. And so we'll plug those points in for x and y. By the way, if you wanted to solve, you could have used this point, which would have been 2 to the right, but 3 down. If you plug in either one of those, you should get the same answer. Now, why is it the same? It's just because the y squared, it's 3 or negative 3, whichever one you want to use. When you square it, it doesn't matter. We're going to get the same number. We're going to get a 9. That looks ugly. Let me try this one more time. Whether you chose positive 3 or negative 3, when you square it, we're still going to get the same value, 9. So 3 squared is going to equal 4 times p times my x, which is 2. What is 3 times 3, or negative 3 times negative 3? 9. 4 times 2 is 8. And so to isolate the p, how would I get rid of a multiplication of 8? Not divide, yeah. Since I'm multiplying, I need to divide there. Do the opposite operation. So we've discovered what P is. That's what we're trying to find here. How far from the vertex should the filament of light will be placed? So that is saying the P value. That's what we're looking for, is the P. And so on this problem, our answer would be 9/8 of a centimeter, which I believe if you put in the calculator is 1.125 centimeters. And that would be our solution. Now, I will have a DOL that goes over this same concept. But before I allow you to work on the DOL, I'm going to kind of walk you through one more that's a little bit more difficult. So if you want to work the DOL now and you're watching this later on, just pause the video. But what I'm going to do here is I'm going to walk you through a harder one. And then I'm going to let you come back and work one just that models perfectly what I just did. So here I'm going to take a look at example 3. It says parabolic arches are known to have greater strength than other arches. A bridge with a supporting parabolic arch spans 60 feet with a 30-foot wide road passing underneath the bridge. In order to have a minimum clearance of 16 feet, what is the maximum clearance? So here's my parabola. Remember, this would be called the directrix up there. That's what you would call it. It's a source of strength where you drive. So the first step is always to write down the equation. So I go to parabola, and I would copy this off. Now, if you did not know, this is a vertical parabola because it's opening downward. For that reason, I'm going to put the 4p next to the y. So normally we just copy a blank formula without the x minus h and the y minus k. But I can just see this image. It's going to be a vertical parabola. So I went ahead and selected the formula that has the 4p next to y. That's because the focus would be moving up and down and all that. Now in their image, they labeled a few of the values, but they did not label some others. What it said is the minimum clearance, so that no matter what, where you're on the road, you have at least 16 feet. I'm going to label that here with a red line. If the minimum clearance is 16 feet, that means on the side of the road, and I'm going to use this point as this line as the front of the tunnel. At the very side, you have a 16-foot high parabola. That's what that is saying there. This is 16 feet on either side. That's the minimum clearance. The problem says, what is the maximum clearance? So that's what we're trying to solve in this problem. Is the maximum clearance here, which I'm just going to do a question mark for now. All right, so if you remember what I did last problem is I first copied down the formula and then I started plugging in some points. I'm picking some points. I'm going to make everything simpler, I'm going to treat this as the x-axis. So I'm going to call this point right here 0, 0. And now I'm going to label the parabola. You could label like the sides of the roads, like say this is 15 feet over and all that, but I'm going to only label the parabola. So specifically, let's start with this point over here. If this tunnel is 60 feet wide, how far is it from 0, the center of the road, to the far right? 30 feet. This point is going to be located 30, 0. Now let's talk about this point. So again, I'm focusing on the parabola here. This point is right a certain amount. It's to the end of the road and then up 16 feet. How far right is this if the road is 30 feet wide? 15. That's 15 to the right and 16 up. Now this point at the center, we're trying to find the height. That we don't know, but that is the vertex, which we label as h, k. On our problem, all we know is that since it's at the center, the h is 0, but the k is unknown. So what we're solving for is k. That's what we're trying to find in this problem. We could label these 2 points, but you don't need them. I'll switch colors. because we have their mirrored values over there. So like this one would be left 15, up 16, up 16, and this point would be left 30, up 0. But you don't need those, so I'll just leave them in green. All right, so how would I solve this? Well, I'd start plugging in values. Since my h is 0, this is going to become x squared. We don't know for p. We don't know our k either. So my formula simplifies to this, since h equals 0. We get that value. Okay, so what's different on this problem is, remember, x and y can represent any point. So these are x's and y's to plug in. But this time I'm still going to have two variables. In the previous problem, I told you this one's going to be a little harder. The previous problem, we only had one variable when we did this. We had an x and y to plug in, which left us with the variable p. This problem, we could plug in an x and y, but I would still have variables p and k. So here's an algebra rule. If you're solving for two variables, you need more than one equation. So why did I write down 2 points? It's because I knew I was going to need 2 equations. To solve this, I need 2 equations. So I'm going to break this up here. We'll do it twice. Okay, so the first one, we'll plug in this one first. I'm going to call this x1 comma y1. And so we'll plug in the x is 15, so 15 squared will equal 4p times the y is 16, y minus k. And then I'm also going to go back up through here, and I'm going to plug in the second point. We'll call this one x2 comma y2. So I'm going to plug this in. 30 squared is my x equals 4p times my y is 0, so 0 minus k. Now you might ask, okay, so what was the algebra trick? If you wrote down 2 equations, how do you solve it? Well, you solve for what is shared and you substitute or eliminate. I'm going to use substitution. I'm going to say, hey, I see both formulas have a 4p. So my goal is going to be solve for 4p. I'm going to solve for 4p on the right side. I think it'll be easier. 0 minus k is simply put negative k. And so if I wanted to get 4p isolated, all I need to do is divide by negative k. And so what I discover is that 30 squared divided by negative k equals 4p. Now that I know 4p, I can substitute right here. So 15 squared will equal 30 squared divided by negative k times 16 minus k. Now we could do the algebra or we can use the calculator. I'm just, for the sake of today, I'm going to use the calculator. So I'm going to come over here to my Desmos graphs. I'm going to just choose nsolve because I want to nsolve a problem here. And I'll type these values in. Let me slide this over so I can see a little bit of it. It says here, you plug in, just nsolve, you plug in the equation as given. Except the one thing I should write in there is you need to use the variable x. So I'm going to say 15 squared, which you could have said 225, equals 30 squared, which you could have wrote 900, over negative, I'm going to insert an x, times 16 minus x. So step 1 for my nsolve is you type in the equation exactly as it's shown you. And then it says you graph y equals the left side of that equation and y equals the right side of that equation. If you have a constant, the intersection will be the solution and it'll happen on the y-axis at that height. So I do have a constant, it'll be at 225. If I zoom out, 225, that's where the solution will be. We just discovered that k has to be 21.33 feet. K is going to equal here 21.333 feet. And that's what we wanted originally, was the maximum height. And that's what we discovered. This here, has a maximum height of 21.333 feet. And I'm guessing that's a repeating, but I'll say maximum height, because your DOL is going to be rounded to the nearest hundredth. I'm going to round this to the nearest hundredth. I'll just say it's 21.33 feet. That's the maximum height, or the maximum clearance if you want to use that terminology. Since that's what they use in the problem, let me write the same: maximum clearance. All right, gone through that. I'm going to let you try one. So yours is going to be easier. I'm not going to make you do what I did there. I want you to solve this problem. Make sure you use your parentheses to begin with. Find 2 points and solve from there. DOL number 1. All right, now let's take a look at an ellipse. So if you look on these pictures, just some basic points. Vertices are the points farthest away from the center. The co-vertices are the points on the ellipse that are closest to the center. The distance to the focus, or the foci, talking plural, is the distance of C. So 2 foci, from foci to foci, would be 2C. From vertex to vertex is what we call the major axis. The minor axis is a co-vertex to co-vertex. Here, before we start this problem, just a general model. I'm going to talk through what this says. Okay, it says that anything that's orbits around the sun is placed at the vertex. We mentioned that in lesson 7 too. The sun is placed at the vertex, and the orbit goes around it. The sun is not at the center; it's at the focus. And so, as we go around, you will have 2 vertices. The point when the sun is closest, the vertex, that's where the sun is closest to the vertex, is called perihelion. Aphelion is when it's the vertex that's farthest away. So when this planet orbits to where it's the farthest away from the sun, it's at this point of aphelion. That's what they call that. The formula for this is A plus C. So I'm going to make sure you catch that here. Aphelion is A plus C. A plus C is aphelion. A minus C is perihelion. Okay, so now let's talk about Hayley's Comet. So Earth orbits around the sun once every year. That's why we call it a year. Hayley's Comet orbits around the sun once every 76 years. Now, why is that? Well, that's because the orbit is so large and it's stretched out so far that happens to occur only once every 76 years. So I'm just going to draw something like that to give you an idea. It's a extremely stretched out elliptical orbit where the focus will be laid out somewhere to one side. Okay, let's leave the problem. It says at perihelion, that's when, according to the previous page, we're at A minus C. That's when the sun is closest to the vertex. So here we go. This is perihelion from here to here. This distance right there is perihelion, which the formula said it was A minus C. The problem says it is 8.8 times 10 to the 7th kilometers. That's that distance there. Now it also tells us at aphelion that, if you've forgotten, was the value A plus C. A plus C is from here all the way to this vertex. So A plus C is that value, and it is 5.9 times 10 to the 9th power in kilometers. That's its distance. And so if I wrote these 2 values stacked on top of one another, you'd probably have a pretty good idea from Algebra 2 what we should do to solve this. Oh, I'm going out of order. My apologies. I need to write down my equation. I have not done that. So after I write these out, I'm going to write down for an ellipse, the equation we work with typically with an ellipse is you'll either have x minus h or y minus k squared divided by a squared minus, plus the other, whether it be x minus h or y minus k squared over b squared equals 1. Because I drew mine so elliptically horizontal, I'm going to choose this to be a horizontal, and I'm going to make the center be located at 0, 0. So instead of saying x minus h, and again, since I drew this horizontal, I'm going to make x come first. I'm going to make the point be 0, 0, which is going to simplify all this to just simply be x squared. And since the k is going to be 0, this is going to become just y squared. So I'll simplify my problem. All right, so now let's come back over here. Algebra 2 says whenever you have two variables, you can solve as long as you have two equations, which we now have. We learned two techniques, more than two techniques, but two that we use frequently in algebra are called substitution and elimination. Well, we've seen substitution today already. What we have not seen is elimination. Elimination works whenever your equations are set up where they're kind of lined up in terms of variables and like terms, and you just combine your equations across. So here I would have 1a plus another a. How many a's do I have? 2a. I have negative c and a positive c. They cancel, they simplify, and we need to add this value. So now what I'm going to do is I'm going to get a blank graph from Desmos. So I'm on my sheet, and I'm just clicking this blank graph right there. And I'm going to type in the value 8.8 times 10 to the 7th power plus 5.3 times 10 to the 9th power. Now that's our value for 2a. I'm going to come back and I'll show you a trick with Desmos here in a second. So I'll just write this down, that 2a equals 5.388 times 10 to the 9th power. This would be in kilometers. Now, if we were going to solve for a, how would you isolate it? It's being multiplied by 2. You would divide by 2. Okay, Desmos can really help us out if we store our variables. Well, how does that work? What I'm going to do is just say a equals, and I'm going to take all this, highlight it, and press the division, and put a 2. And now the calculator has stored. So I don't ever have to type this number again for the calculator. I just have to put an A, and it's going to know it's that value. It stored it. Okay, so now I know A is 2.694 times 10 to the 9th. This would be in kilometers. The formula wants a squared. Let's figure out what that is. Ooh, let's round this to the nearest 10th. So I'm going to say this problem, we will have x squared over, I'm going to say call this 7.3 times 10 to the 9th. This will be in kilometers, this equation. All right, so we continue on. I don't know b squared yet. So that we'll be looking for in a second. But I found a. So what can I do? Well, now that I know a, I could come back here and solve one of these equations. I'll just take the second one because it's positive numbers. I like working with positives. If I take the second one, we can now say if a plus c equals that 5.3 times 10 to the 9th kilometers, how could I isolate this c? You would subtract a from both sides. And so what I'm going to actually do is type in the calculator exactly what I wrote right there, because the calculator knows what a is. So I'm going to say c equals 5.3 times 10 to the 9th minus a. And now we get the value c. C is 2.606 times 10 to the 9th And this is in kilometers. By the way, C, just so you know, is always the distance from the center to a focus. That's the distance C. That's what you just saw for. This distance from here to here is that number. A is the distance from the center to the vertex. So it's a larger number than C. All right, well, we now know A and C. The formula wants B. If you remember from the formula chart, anytime you're dealing with a ellipse or hyperbola, we have an ABC relationship. For ellipse, the ABC relationship, this is for an ellipse now. Let me scroll over so you can see both words. Ellipse, the ABC relationship is that C squared equals minus B squared. So I'll write that down. C squared equals A squared minus B squared. Since I'm solving for B squared, truthfully, all I need to do to get B squared by itself is I will add B squared to both sides, and I will subtract C squared from both sides. If I do that, the C squares will simplify, the B squares will simplify. I'm left with B squared will equal A squared minus C squared. I'm going to type that in the calculator to get my solution right there. Oh, I just realized I wrote down A. Oh, no, I did square it. Okay, sorry. Blank there for a second. Yeah, that is A squared. Okay, so now let's get B squared. It'll equal A squared minus C squared. That will be our B squared right there. The A squared was supposed to be to the 18th power. That's why I knew something was off when I saw the 9. That's what was off. I put the wrong power. That needs to be an 18. Sorry about that. 18 was our power for A squared. And then B squared we just found out is 4. I ran last time around to the nearest tenth. So let me do the same here. 4.7 times 10 to the 17th power. And again, this would all be in kilometers. And that's my equation. So, word problems. The advantage is you get to pick points like the center and things like that. The disadvantage is the word problems do not give you the mathematical equivalents for everything. You kind of have to figure it out as you go. I understand this problem had huge numbers and it made life more difficult. For you, your DOL is going to be much simpler. For DOL number 2, I want you to use this, and I'll just kind of read over it just so you make sure you understand. Ellipsoids, 3D ellipse, are used in healthcare to avoid surgery and treatment of kidney stones. An elliptical lithotripter emits underwater ultra high frequency shock waves from one focus, so there's a focus, with the patient's kidney carefully positioned at the other focus. If the ellipse used to generate the ellipsoid lithotripter has a major axis, 12 feet, and a minor axis of 5 feet, how far should the patient shockwave source be set apart for maximum effect? As a reminder, the way ellipsoid works is if something is emitted from one focus, no matter which path it takes, when it hits the wall, it'll reflect to the other focus. So what they are asking you to find is how far apart should these two focus be separated, or this person's kidney from the source. That is a length of one focus to a second focus. From foci to foci, do we call that 2A, 2B, or 2C if it's 2 foci? Question, would this be 2A, 2B, or 2C? 2A would actually be vertex to vertex or major axis. Major axis will be your 2A. Let me ask this, what's minor axis? Major axis is 2A. Minor axis is, very good, Hayley, 2B. So what is foci to foci going to be? That's 2a, that's 2b. What's this?
C.
2c. You're going to try to solve for 2c. That's what you need to solve for, 2c. There's your 2a, there's your 2b. You're going to try to solve for 2c. Don't forget about your foci or your ABC relationship. You won't need the actual formula for an ellipse in this problem, but you will need your ABC relationship for an ellipse right here. You will need that formula. All right, DOL number 2. Let's talk about hyperbolas. As you look at the picture, you can tell hyperbolas have the most going on. Between, here's your center, you have these co-vertices that they place at these 2 points. I place them on these 2 points. Either way, the co-vertices are not on your hyperbolas themselves, but the vertices are. Just like a parabola, the vertex is the center or the reflection point of each parabola if you looked at them individually, but they're technically hyperbola, which means they're mirroring each other. Transverse axis connects vertex to vertex. Conjugate axis would connect these asymptotes vertically through the vertex. And the foci, again, would be on the inside. So with all of that, let's see how they're used in the real world. Location, location, location. That's how hyperbolas are used in the real world. People apply these to find the location of objects. So I'm going to swap a little bit of the verbiage here. Because when I wrote this problem, I used to do this later after covering chapter 8, 9, we went out of order. So this problem, I'm going to actually change the last sentence. I don't think it'll let me type onto it. Oh, it does. I'm just going to say find the location of each station. Find the location, not of the station, I'm sorry. Location of the boat. Round to the nearest whole number. All right, there we go. Got my instructions that I want. So if I'm going to solve this, we need to know something about the boat. The boat, it says right here, is 60 miles away from the shore, and it's going parallel to the shore here. There's 2 transmitting stations. So each station sends out a beacon. You've seen these in the movies. They kind of do that beep, and they send out something, beep, send out another one, beep. You know what I'm talking about? Well, they do this simultaneously, which means as this one's sending out a signal, the other station is doing the same, beep, beep, all at the same time. What happens is the boat picks up signal 1, or I'll call it signal 2 because it has S2 there, before it ever picks up the one from the second place. And then it's going to go off the timing difference to figure out exactly where it's located. That's how hyperbolas are used in the real world. So with that, I'm going to take off some of these circles, and I'm going to draw through just a general hyperbola. The hyperbola would be that signal as it gets sent out, leaving the stations. That's how as this kind of goes out this way, you would treat it like a hyperbola and solve. Let's pick some points out. Oh, sorry. Horizontal hyperbola. Let me go to hyperbola. We want the horizontal one. That means the a squared is underneath the x. So I'm going to take that formula. X minus h squared over a squared minus y minus k squared over b squared equals 1. So now let's label some points. I'm going to choose the center to be 0, 0. That point right there is going to be 0, 0. That is your h comma k. So what that immediately does to my equation is it makes it just simplify to be x squared and y squared. Now, the stations are the foci. That's the reflection point or the point that's sending out the data. The foci is always a distance of c. Now, since this is foci to foci, 2c would be 200. What does 1c equal? you're not sure what I'm going to do here for this problem, so I'm going to do a blank graph. Just going to erase this here and just type it in. C is going to equal 200 divided by 2. So that's the distance. Let me see. I'll do it like that. That's the distance from the center to the station. So since it's 100 units away, I could say this station right here, this foci, if you needed the point, you could say that point is going to be 100 to the right, comma 0. This one point over here would be negative 100, comma 0. So those are two foci points listed, and we have the center, but the foci is not going in for a squared or b squared. Now here is the real world trick or application of hyperbolas, and that's this, that when they send up these beacons, when they pick up the difference in time or the difference, it's always equal to 2a. So I shouldn't say difference in time because it's actually 2 times the distance of a, which a is center to vertex. So when these hit, that's how the math's going to be solved. The difference will equal 2a. This problem said the ship is between the 2 stations and it's 50 miles closer to station 2 than station 1. I'm going to hit this right here in red, 50 miles closer. That value right there is our difference. So our difference equals 50 miles. So I'm going to come back over here, and if 2a equals 50, let's solve for a. A would be 25. In case you didn't know the math, by the way, what you could do in the calculator is just type in a equals 50 divided by 2. Now, I want you to follow. This is very important. I'm showing you a huge trick here. I'm programming Desmos as we go. Desmos now knows C is 100, and it knows A is 25. That's really going to help me out. My problem, I can plug in a squared. A squared is going to be 625. So we come to our formula, and I'm going to say a squared is 625. Now let's talk about the b squared. We don't know b, but we do know c is 100. We know a is 25, and this is in miles. We could solve for c using the ABC relationship. On the formula chart, for a hyperbola, it says the ABC relationship is that c squared equals a squared plus b squared. C squared equals a squared plus b squared. You could plug in your numbers, but I'm going to use Desmos that is stored. But basically what I'm trying to solve is that 100 squared will equal the c squared, just 25 squared, plus b squared. And so we will subtract that 25 squared from both sides. You can't combine like terms there. They're going to be different. But 100 squared minus 25 squared will equal our b squared that we plug in right there. On here, you don't actually have to even type that part in. What you could just do is c squared minus a squared. C squared minus a squared. Notice that'll be the same value. It's 9,375. Oops. 9,375. There's my formula. If you needed a formula, that would be a solution. We're looking for the location of the boat. All right, so let's just talk about the boat for a second. All we knew about the boat was that it was 60 miles offshore. Is that an X value or a Y value? That's a Y. What we don't know is the X. If you wanted to solve it, you could plug those numbers in and do some algebra. I'm just going to let the calculator do the algebra for me. So I'm going to take this equation and plug it in, and it's like the insolve problem, but I'll just do it from here since I already have this programmed. I'm just going to type in the formula, x squared divided by a squared. It knows what a squared is. It's already programmed. Minus, I guess I could name this B. Now I only have to type in the B. Okay, minus 60 squared over B squared. So all this is programmed in Desmos. That it knows what A is, it knows what B is, equals 1. And then so the way you do in solve is you say y equals the left side. And then you do y equals the right side. They will cross at the height of 1. Let me expand this out. There's the intersection. The value here is 25. So this is saying it's 25 units to the right, which I'm thinking, one thing that's a little strange here is I thought the number was off. Did I type in something wrong here? 60 squared, 625. Well, it doesn't look like it, but we're getting that their x would be 25 units to the right. I have that C is 100, A is 25. C squared minus A squared is oh, that's B squared. I need to do this real quick. The square root of this would be B. Whoops. Let me cut this. There we go. That's B squared. And so when I look at this, B is 29.4 miles. So I needed to square root. That was B squared. That number is correct. But when I put it in the formula, let me make sure that's right now. B squared, 9,375. Yep. So when he puts in the formula, 29.4 is our solution. So this would be how far out the boat is. That boat, find the location of the boat, would be 29, what do we say, 29.4? It says to the nearest whole number. So I should say 29, comma, 60 would be the location of the boat, and this is in miles. All right, so I know there's a lot there. I have way too many problems for this unit. So let's try one more here. I just plain out have way too many here. But I have 2 more to go and then a DOL. I'm just going to try to get through 2A because 2A is more realistic. Why do I say realistic? Because in a real world problem, most boats don't know necessarily that they're exactly 60 miles away from the shore. So there's 2 unknowns. And if there's 2 unknowns, you need to have, who remembers how many equations? If you have 2 unknowns, you have to have 2 equations. So this next problem walks you through that. How do cell phone towers spot you on your GPS? Well, they have to have 3 towers. The way it works is they're going to set up, I'm just kind of skipping through the problem a little faster here since we just worked through it, 2 separate hyperbolas. So they have this hyperbola and they're going to have this hyperbola going this way. They'll have 2 separate hyperbolas. So again, it's one station sending out a beacon and another station sending out a beacon. But all of that is where they would get these hyperbolas, is from these beacons that are going out. Okay, and so you'd have these hyperbolas when they measure just half the circle against each other, semicircles. Okay, so here's what I'm going to do first, is since I'm working with hyperbolas, I'm going to copy down the blank portion of the formulas. So for a hyperbola, you have a minus. Now we need 2 formulas. So we're going to do this twice. You may. To keep Desmos track of things, I'm going to clear this calculator here. We're going to use Desmos for a lot of our calculations here. I'm going to call the A and B, since I'm going to have 2 of them, A1 and B1, A2, B2 for my equations. So we'll do the blue as A1, B1, the red hyperbola that I started to draw as A2, B2. Okay, let's plug in some points. I'm going to call, it looks like a first quadrant here. I'm going to call this 0, 0. So let's talk about the center of the blue hyperbola. If it's 100 units all the way to the top, I think that would be 50 right there. That's going to have the center value of 0, 50. It's a vertical hyperbola, which means y needs to come first, and it's minus 50. The x isn't to the left or the right, so it'd simply be x squared. For that red hyperbola, the center would be 40 miles over. So it would be 40 to the right, so 40, 0. Since this is a horizontal hyperbola, it would be x minus 40 and simply y squared. Y is not shifted up or down. It's a value of 0 there for the k, so it'd be y squared. So there's the general form of these two formulas. And what we could also state is the c values. The c for the blue here is the distance from the center to the foci. That's a foci there. So c, I'll call it c1, is going to equal 50 miles. Over here, from the center to this foci, it would be 40 miles. So I'll call that C2 is going to equal 40 miles. So I'm going to plug that in real quick so the calculator has them stored. C1 is going to equal 50. C2 is going to equal 40. Desmos now has that programmed. Now in my formula, it tells us that the difference is going to equal the rate times the time. You can kind of read through all here. It's the same setup as the last problem. So we already know that the difference is going to equal 2a. I told you that last time. That's the application of hyperbolas. Difference is always 2a. Well, this problem says the difference you can calculate by, if they hear it at different times, it's the amount of time times the speed at which the beacon's moving. So if you multiplied those, you'd get the difference in the distance. Difference in the distance would be r times t. Well, notice we have two things set for d. So I could substitute and say, okay, 2a will equal the rate times time, or if I divide both by 2, I could discover that a is going to be equal to the rate times time divided by 2. All right, so let's go find first A1. A1 is going to be the rate, which they give us the rate here. These beacons are moving 980 feet per second. And it's going to be all divided by 2. Let's see how much time takes place. Okay, so A1 is going to go with the vertical hyperbola. So I'm going to look for the difference in time between beacon R and O. It says the Loran receiver, long range receiver, that Loran here, on Sloop Gloria received a signal from O this time after the signal from R. Okay, so O and R, you get this time right there. So I'll plug that in. 323.27. And I'm just noticing we're going to have a units problem. This says feet. These do not say feet. We need to convert those as well. Feet, you would need to convert it by, there's 5,280 feet in a mile. I'm just realizing this, that we're going to have this conversion. It's not going to change much for math. It'll be real easy. This will get us to feet over 1 mile. So what I need to do on my calculator is just multiply these times 5,280. 5 tomatoes. There's 5 tomatoes in 1 mile. 5 tomatoes. 5,280s. We'll play on words there. Anyways, that's how many feet they are. Now we convert it, so we're good. So I come back to this problem here. Let's find what A1 is. So A1 will equal the 980 times 323.27 milliseconds divided by 2. That's our value for A1. And now let's find the value for A2. A2, and again, I'm using this formula up above. It's the rate, which they said is 980, times some amount of time divided by 2. Let's find out how much time there is. It looks like, and this amount of milliseconds, that's the signal from Q. So this would be times 258.61 milliseconds. That'll be your A2. 980 times 258.61, and all of this divided by 2. There's A2. Now, the last variable I need to solve for here is I need to solve for our B's. Remember that they follow the ABC relationship, and that formula from earlier was that C squared equals A squared plus B squared on a hyperbola. C squared equals A squared plus B squared. And since I'm trying to solve for B, the first thing I'll do for both of these formulas is I'll end up subtracting A squared, which means C squared minus A squared will equal B squared. But for Desmos, I need to get B by itself. And so I'll end up taking the square root of both of these. Usually we'd add a plus or minus. Because this is distance, it's only going to be the positive. B will equal the square root of C squared minus A squared. Okay, so for both of these formulas, this will be the same. So I'm going to type in B1 here will equal the square root of C1 squared minus my A1 squared. There's the value for B1. And B2, well, let me just copy this. It'll be easier if I just say copy and change this. B2 will be everything changed to a 2 instead of a 1 because we're dealing with the second hyperbola. There's B2. So how can I solve this problem now? If I graph these, the intersection of the two graphs will be the solution. So I'm going to type in those and we will have our solution. After all this work, we're finally there. Oh, and that's in miles too. This 50 is in miles. Oh no, that's no good. We need to convert this to feet. So this also gets multiplied by 5280 divided by A1 squared minus x2, or x squared, I'm sorry, x squared over B1 squared equals 1. That graph, it's graphing in black. I want to change this to blue since it's how we've been dealing with it. That's our blue equation, or blue hyperbola. And now let's do our red. So x minus, and I have 40 there. I need to multiply this by 5,280. This will be squared. I realize I didn't square this one. Square this one. Numerator. Squared. There we go. Divided by A2 squared minus y squared divided by B2 squared will equal 1. Now let me check and make sure A1, B1, A2, B2. It looks like I got my values. And again, I had to convert from miles to feet. So that's what that number is there. When I zoom out, we should have solutions. There they are. So I can tell you this. We know that it says Q, here's it, O, here's it after Q, and R, here's it after. So the two possible solutions here, it's not going to be this one because this would be farther away from the stations. That's going to be the location. So the location in terms of feet would be these two units. That was a lot of work to get there. A whole lot of work. But that would be the location in feet. Let me slide this over a little bit so I can write down what we got is the location of the boat in feet would be 987,813 1,021,621 1,021,621 21,621 feet north if you're dealing in feet. What an answer. Isn't that nuts? Well, what's nice about doing it once is that you can do it a second time a little bit quicker. So let me walk you through if you were doing this a second time. Programming, why programming can be so helpful is you can set up the problem and solve kind of the same way if you wanted to do it a second time. Notice the problems would change here is that they're giving us different center points. So I could come through and say, oh, this time around, my vertical would be 0,40 miles. So my vertical parabola last time was the y, so I could change this to a 40 here. Whereas the horizontal hyperbola, the center would be located at 100, 0. So I could put this in as 100. You might be going, there's no way you're going to do this that quickly. I'll show you we can. So we've shifted that over. The C values are from the center to the foci, which means they're now 40 miles. 40 miles. And the other one is 100 miles. Oops, 100 for there. So I've done the C's. The A values here, our time value has just slightly changed. So the first value, O to R, is 323.27, which I kept the same. But this time I changed the second value. So it'd be 646.53. 646.53. 646.53. This math calculates on its own. We look at our graph, and this time you could say, well, is that the real solution? No, it's going to be this one out here. That's going to be your location. How crazy is that number? They just keep getting crazier and crazier. We did all that work. By that I mean very little work. We just substituted in our values, and the calculator did it all for us. That's the power of programming. If you're going to do one job a lot of times, if you program it once, you can keep repeating it. Now, if you follow directions and been doing exactly what I've been doing, let me just say 4.68 times 10 to the 6th and 5.52 times 10 to the 6th in feet. That would be the location of the boat here on this one. If you've been following along with what I've been doing, you'll be able to do your DOL really quickly because it's the exact same problem. I've just swapped some values around. Projectile motion. So lesson 7.5, we talked about projectile motion, specifically how you can model something moving through the air. And these were the two equations that you've given you. Now we have a calculator for this. It's calculator number 23. And I'm going to walk you through, not the algebra. Today's been a big technology day. I'm going to use the calculator here. We could do the algebra, but it's kind of tedious. I'll kind of show you how you would do it in a second, but I'm going to open up calculator 23. If you use my calculator for projectile motion, there's really 6 values that you can fill in, but not all are needed. What are needed are your initial velocity, the angle, the initial height, and the gravity constant, depending on meters or feet. I had mentioned over here that gravity can be 32 feet per second or 9.8 meters per second squared. So in our problem, Terion shoots a basketball at a velocity of 30 feet per second. So he's going to shoot a parabola of a basketball, something like this. And that initial leaving his hand, he's shooting it, it's 30 feet per second. I know those don't match up perfectly, but we're going to say that. 30 feet per second. I'm giving you a physics drawing over here. These are the values we're going to type in. It says this angle is 48 degrees. That's my theta. He released the ball at a height of 8 feet. So if I were going to do a little stick figure here, he released it, and that height on that ball is 8 feet. So jump shot, there's the ball, and it's going to fly through the air, and he's going to make the shot, nothing but net, swish. So if you don't know, a basketball goal happens to be 10 feet tall, so I need to be a little bit higher here. And so here's the basketball goal, and he's going to swish this shot, and the basketball goal has to be 10 feet high. Now, to solve this problem, I told you need these 4 values, which we have here. Initial height is 8. And since we're in feet, we're going to use the gravity constant 32 feet per second squared. Those are the values that we type into my calculator. So I'll get these in here. From this, everything you need can be graphed on the, you'll see it drawn as a red parabola over here. So there's the graph. You might notice, though, there's this blue portion. What I programmed in is depending on the problem, it can represent anything. This is going to represent, for our problem, the basketball goal. All we know about the goal is that it's 10 feet high. If you open up this end result, that's talking about where the ball is supposed to end up. I want you on the y height to put 10 feet. You can leave the x alone. If you notice, the x is just showing how far is it away. We don't know the answer to that. I'll leave it there for now because that looks pretty good. As I'm zooming in, that looks really good. But what you could do is after you get y vertical to equal 10, in this folder, if you scroll down, you'll see that there's different options for solving. You could solve it after the projectile went a certain number of feet. Well, we don't know the number of feet. We're actually looking for how far away was Terion from the basketball goal. That's what we're trying to figure out, is what is that distance? So I'm not going to look for a projectile when it reaches x distance because I don't know what x is. The next says projectile when it reaches y height. Now that's going to be the answer. We know that the y value is going to be 10 feet high. So we're going to solve for when this gets 10 feet high. The answer is at y height, Terion is 26.03631 feet away. That's my solution here. To part A, it's going to be 26 feet. I'm just going to say 26 feet. Now part B, I'm not even going to get to, but what it's going to say is how long the ball in the air. And that's the time value right above it with it. The time would equal, and I'll go to the nearest thousandth, 1.297 seconds. That's how long the ball's in the air. This was the part A. This is the part B. So I said there's 6 values that you could type in my calculator, and I only wrote down 4 things. The other 2 that you can put in are an x distance and a y distance. In our problem, we knew y was 10. It was coincidence that I just kind of scrolled really fastly on the x, and it happened to be 26. And that's why the ball seems to travel right through there. Now I want you to see something. Please follow along. I want to make sure you're processing. If the goal were there, does Terion make the shot? Now let me interpret this for you. The ball goes up and it's going to hit the ground before it even makes it to the goal. Okay, what if the goal was right here? Does he make the shot? Now we don't know about the backboard, but if there's no backboard, then he shot it over the goal. So just making sure you understand what that represents. It was just coincidence that when I dragged that really fast, it ended up at 26 the first time. But that's, you don't have to type that one in to solve this problem. You just go to y distance. All right, your turn. I want you to solve DOL number 2 here about the flight of the baseball. I would recommend you type in all 6 values and look at the picture to help you interpret and solve.